Now that we have taken our Teach Pendant program from RoboGuide and put it onto a USB drive, we are going to load it up onto our actual robot controller and then take a look at some other program refinement features. Typically in industry, 70 to 80% of programming is done offline, but there are still touch-ups and things to refine and fix and streamline when we're actually programming the robots on the physical or in the physical work cell. So the first thing we need to do is I plugged in the USB drive with the .tp file into the USB drive on the controller, not the one on the Teach Pendant. Don't use that one, use the one on the controller. And we need to set the directory for that. So we're gonna go to Menu, scroll down to File, scroll over one, and when you select File, hit Enter. And you might see UD1 at the top, and you might not. So what we need to make sure we do is set the directory for pulling that program off the file. So what I'm going to use is F5 utility, and it's going to say set device. I'm going to hit enter, and then here it gives you all the different options. And we looked at these before. There's from a backup, from a memory device, from USB on the Teach Pendant or USB disk in the controller. We're going to choose USB disk on the controller, hit enter. And then it says press directory to generate the directory. Hit that. Basically what this is asking for is what programs do you want to pull off. It usually depends on what device you're pulling from, but we can actually scroll over and select .teach pendant programs or other specific files, or we can use the asterisk here and pull everything, load everything from that directory. I know for a fact that there's only one .teach pendant program on there, so we're just going to hit up everything. And we're going to see system volume information, and we're going to hit load. Now that we have loaded up our directory, we can see at the very first thing at the top, we have my program, MDBox. That's going to be on the, we're going to load that up onto our Teach Pendant program. So I'm going to hit load mdbox.teachp, hit yes, and then it says that it's loaded. So to confirm this, we'll go to select, and then we'll find our program, and sure enough, MDBox, this is the simple 6-point program that I created before in RoboGuide. So now here's the fun part. We get to test out our program in RoboGuide. And the first thing that we'll want to do is we'll step through the different programs, but we also want to make sure that we can easily see how our program's lining up between what we tried to do in RoboGuide and what we're trying to get across on the actual robot. So one trick I'm going to show you is embedded in this gripper, there's actually a digital output or a laser, and you can go down to I/O, and if you don't see robot I/O or digital I/O, you can always go to type and scroll down and find digital I/O. And what you'll see, these are all digital outputs. So some of them are related to the lights on the controllers for cycle start. Some of them are related to the lights on the safety fence and area scanner. We're going to hold down shift and page all the way down to DO101. And that is actually going to turn on our laser. And then there we can just hit on. And you can see we have an embedded laser built into our grippers. Just like we program robot I/O, if you go back to our program, we can also program digital I/O. So it runs through the same process where you go to new instruction, I/O, and we've chosen robot output before. We can also choose digital output. So it runs the same way. But what we're going to do is use this laser to really help pinpoint how well our program translated to the physical robot. So I'm going to put it into step mode, hold down my dead man switch, hit reset, hold down shift, and I'm going to step through each individual part. Now with our program loaded from RoboGuide, we're going to step through it and test it out to see if we need to make any adjustments. So I'm going to hold down, I'm going to press the step button, hold in my dead man switch, hit reset, hold down shift, and I'm going to move forward with each individual point. So there's my home or first position. And when I go to my second position, you can see I'm not quite to the corner of the box that I wanted to be at. And that's okay. Again, 70% of this is done with offline programming. That rest of that 30% in terms of at the robot, you do need to touch up points. And that's a really easy thing to do. So staying in world mode, we can then use our laser to help guide us so we can get to the right point, and we're going to make sure we're still on the specific point that we want to touch up. So all I'm going to do is adjust over and jog the robot to exactly where I want it to be, right on the corner. And when I do that, I'm going to keep holding down shift and then press this button here, touch up. And you're going to see the position has now been recorded to point 2. So we've changed the data for point 2 within this program. If you want to verify that, you can always go hit the back button, then go back forward, and you'll see we now have gone to the new position. From here, it's really easy to check and see. If we go to the next one, you see we're off to the left a little bit, so I am going to jog it back right and a little bit forward. Hit shift touch up, and then go to the next one. Again, some adjustments need to be made. Going to the right, back a little bit, hit touch up, and that could be the soft key or the screen. And then if I go to forward on my program and back, you can see I also need to make some adjustments here. And now if you try hitting touch up without hitting shift, you will get a warning that says press shift key to record. So you press shift, then do that touch up, and then go into the last one. And that one's way off, so we're going to go back. So this is one where you can go back and you can touch up here, or you can use that same point from point 2. So let's do that. I'm going to change this to point 2. And then I want to return back home. I'm just going to simply add a new move point. And I'm going to go and change that data to point 1. All right, now we can test out our program, function aboard all, and scroll back up to the top. And then I'm going to take the step mode off, and let's test out our program. You should see now that it will go to all of the newly touched up or defined points. But as you're watching this, hopefully you notice something. I'll step through the program one more time. As we're going from one point to the next, you should notice something a little bit peculiar about the path of the robot. And then the main thing with what's happening is you're probably seeing an arc that's happening in that robot motion. And that's because we are currently, all of our points are moving in joint mode. Just because we jog the robot in world mode, where we get this nice, neat X, Y, Z Cartesian coordinate system, that's just how we move the robot in the real world. how we program the robot. Again, programming is all about record the point and define how the robot moves. So when we record these points in joint mode, that's where the servo motors are going to move in the most efficient way to get from point A to point B. And arguably, it is faster. It is faster for them to come at a curve and to come at an angle, and I'll demonstrate that now. So you'll see our first point from home to the first point here. You can see that curve motion come into play, and you'll see a curve there. You see a little bit one here, and this one's a pretty drastic one. So what we're going to do now is we're going to go back, and we're actually going to change some of these motion types. And then you'll really see the difference of why we sometimes use linear mode versus joint mode. So I'm going to put it back into step mode, and you've seen this before. We actually just move over once, and then I'm going to change, instead of J for joint, I'm going to select linear. And you'll see right away that the linear does change the rate of how quickly the robot travels, and it'll be in millimeters per second instead of percentages. Typically with this robot, we keep all of our programs under 250 millimeters per second to avoid any DCS errors. For this one, I'll do 200 millimeters per second. And for the purpose of this section, we're going to keep it at fine, so it goes to that direct point. Please keep in mind that this is a really important reminder to check your speeds, because these robots can move 4,000 millimeters per second. So really, really fast. We always need to be mindful of our speed and termination. So I'm going to go to my next point. And here, that's a linear motion now. We go to the next one, the joint, or point 4. We're going to do the same thing. Change that to linear and adjust the number to 200 millimeters per second, and we'll leave it at fine. And then we're not going to make any other modifications, so we'll scroll right back. And then for our last one, at least in this section, we're going to keep that, we're going to go linear with that as well. All right. So what you'll see now, and I'm going to keep the last one at an arc motion, or that joint motion. Now when you see we go through our program from the beginning, you're going to run into, I'll take it off of step mode. Watch how the laser moves with around the robot, or around the square. The big difference is going to be in that last motion where it's still using that arc movement. Now we can adjust our speeds. 5% is typically the max for these DCS parameters. We can go up to 250 in terms of linear motion. The other thing that we can do, which is kind of fun to play around with, is we can do continuous motion. And that's where we actually have our robot cutting corners. We mentioned this earlier. We can put in so it will not actually stop at the individual points, but it'll do more of an obstacle avoidance. So now you'll be able to see the difference with, I'll keep it back in step mode. You'll see the difference from moving from continuous to fine motion. All right, so here's our first continuous movement. And then it'll really look interesting when we actually pull it out of, pull it out of step. Thank you. So you can see there's no stoppage at each of those individual points. And then depending on the speed and how much our angle is of approaching that particular point, you could actually see some pretty significant, a pretty significant arc in between from one point to the next.